Have you ever tried to watch a video about quantum physics and felt completely lost after just a few minutes? 1 second it's talking about particles, the next it's waves, then something about cats being dead and alive at the same time. Your brain starts spinning, and you think this stuff is way too weird, not for normal people like you. Most people hear words like superposition, entanglement, observer effect, and they just switch off. Quantum physics seems confusing, mysterious, almost like magic that only super smart scientists with advanced degrees can understand. But here's what nobody tells you. Beneath all the jargon and strange experiments lies one simple, powerful shift in how we think about reality itself. Once you grasp this core insight, everything else, the weird behavior of particles, the famous paradoxes, the seemingly impossible experiments, all of it starts to make perfect sense in its own strange way. That single shift changes quantum physics from a chaotic mess of confusing facts into a clear, connected story about how the universe actually works at its deepest level. That core insight is this: reality at the quantum level isn't made of solid, definite things following fixed paths. Instead, it's made of possibilities that only become definite through interaction. Everything exists as a spread of potential until something, a measurement, a collision, any interaction that creates a relationship, forces one outcome to emerge. The universe isn't a clockwork machine. It's relational, probabilistic, alive with potential. When you see quantum physics through this lens, the strangeness doesn't go away, but it stops feeling random or impossible. You start to recognize the same pattern showing up everywhere: waves of possibility, collapse into definite states, and deep connections that transcend distance. Let me show you exactly how this works by walking through the discoveries that led scientists to this revolutionary understanding. The journey begins in the early 20th century when physicists were studying light and tiny particles like electrons. They expected these things to behave like miniature versions of everyday objects. Little solid balls that exist in one place, follow clear paths, and obey predictable rules. But experiments kept showing something disturbing. These tiny things didn't behave like balls at all. Sometimes they acted like particles, solid and localized. Other times they acted like waves, spreading out and creating patterns that only waves can make. Take light. Shine it through 2 narrow slits onto a screen, and you don't get 2 bright lines like you'd expect from particles passing through. Instead, you get alternating bright and dark bands, an interference pattern. This happens when waves overlap. Where wave peaks meet peaks, you get brightness. Where peaks meet troughs, they cancel out, leaving darkness. Water waves do this, sound waves do this, and apparently light does this too. For over a century, scientists assumed light was purely a wave, rippling through space. But then other experiments showed light also comes in discrete little packets called photons. It can knock electrons out of metal surfaces, one at a time, like tiny billiard balls, hitting a target. Einstein won his Nobel Prize for explaining this particle-like behavior of light. So which is it, wave or particle? The answer is both, and neither. Light, along with electrons and everything else at the quantum scale, doesn't fit into the categories our everyday experience prepared us for. The same photon can display wave properties in one experiment and particle properties in another. More shockingly, it can display both in the same experiment, depending on what you choose to measure. This is where the famous double-slit experiment becomes truly mind-bending. Send photons one at a time through the 2 slits. Each photon hits the screen at a single point, like a particle. But over time, as thousands of individual photon impacts build up, they form the wave interference pattern, bands of light and dark. Each individual photon somehow knows about both slits and interferes with itself, as if it went through both openings simultaneously. The photon isn't taking one path or the other, it's exploring every possible path at once, like a wave spread across space. Now place a detector at the slits to see which one each photon actually passes through. The moment you do this, the interference pattern disappears. You get 2 simple bright patches, one behind each slit, exactly what you'd expect from particles taking definite paths. The act of measuring which path the photon took destroys the wave behavior. Observation doesn't just reveal a pre-existing reality, it fundamentally changes what happens. This is wave-particle duality, and it reveals the first piece of our core insight. Quantum objects don't have fixed, definite properties independent of observation. They exist as a blur of possibilities. That blur is real, not just a gap in our knowledge. The photon genuinely takes all paths until something forces it to choose one. This leads directly to superposition, the idea that quantum systems exist in multiple states simultaneously. An electron doesn't just have an unknown position we haven't measured yet. Before measurement, it genuinely inhabits many positions at once, smeared out in space according to a mathematical wave function that describes all the possibilities and their probabilities. A radioactive atom doesn't secretly decay at a specific moment we simply haven't observed. It exists in a superposition of decayed and not decayed until something interacts with it in a way that collapses that superposition. The most famous illustration of this is Schrödinger's cat, which sounds absurd but perfectly captures the strangeness. Imagine a cat in a sealed box with a vial of poison connected to a radioactive atom. If the atom decays, the vial breaks and the cat dies. If it doesn't decay, the cat lives. Quantum mechanics says the atom is in superposition, both decayed and not decayed, until observed. Therefore, the entire system, including the cat, is in superposition. The cat is both alive and dead until you open the box. Schrödinger proposed this as a criticism, trying to show how absurd quantum rules would be if applied to everyday objects. But the mathematics doesn't lie. Small systems really do exist in superposition, proven in countless experiments with photons, electrons, atoms, and even specially prepared molecules. The reason we don't see cats in superposition is that large, warm, complex objects interact constantly with their environment, air molecules bouncing off them, photons hitting them, heat radiating away. Each tiny interaction is a kind of measurement that collapses superposition almost instantly. Big things decohere too fast for us to notice their quantum nature, but at the scale of individual particles, superposition is everywhere, and it connects directly back to wave behavior. Remember the photon going through both slits? That's superposition in action. The photon is in a superposition of going through the left slit and going through the right slit. Its wave function spreads through both openings, and the two parts interfere with each other, creating the pattern we see. The wave isn't a separate thing from the particle. The wave is the mathematical description of the particle being in many states simultaneously. This brings us to the observer effect, which sounds mystical but is actually straightforward once you understand superposition. When you measure a quantum system, you force it to interact with your measuring device in a way that entangles the system with the device and ultimately with the wider environment. This interaction collapses the wave function from a spread of possibilities into one definite outcome. Before measurement, the electron is in many places. After measurement, it's in one place, the place where it interacted with your detector. Measurement doesn't mean a conscious observer has to be watching. It means any interaction that correlates the quantum system with something larger, leaving a record, creating a relationship. A photon hitting a detector, an electron colliding with an atom, a particle leaving a trace in a cloud chamber, these are all measurements. They collapse superposition because they entangle the quantum system with the environment in an irreversible way. The double-slit experiment demonstrates this perfectly. When you place detectors at the slits, you're entangling each photon with the detector. The detector either clicks at the left slit or the right slit, creating a definite record of which path the photon took. Once that information exists in the world, the photon can no longer be in a superposition of both paths. The wave function collapses and the interference pattern vanishes. The detector doesn't physically bump the photon in some clumsy way. Even extremely gentle measurements cause the same collapse. It's the existence of path information that matters, not any crude disturbance. This raises profound questions. If measurement creates definite outcomes from fuzzy possibilities, and measurements happen through interactions, then reality is fundamentally relational. Things don't just exist with intrinsic properties sitting there waiting to be discovered. Their properties emerge through relationships and interactions. An electron doesn't have a definite position until something interacts with it in a position-sensitive way. A photon doesn't have a definite path until something records which way it went. The universe isn't a collection of isolated objects. It's a web of interactions, and what we call real are the definite outcomes that crystallize when parts of the web connect in certain ways. This is the heart of the quantum revolution, the shift from thinking about reality as made of things to understanding it as made of relationships and processes, and nothing illustrates this better than entanglement. When two particles interact in certain ways, their wave functions become linked, creating a single shared quantum state. From that point on, they are not two separate systems. They're one system described by one wave function, no matter how far apart the particles move in space. Measure a property of one particle, and you instantly know the corresponding property of the other, even if it's on the opposite side of the galaxy. Einstein hated this. He called it spooky action at a distance and argued it proved quantum mechanics must be incorrect. There had to be hidden variables, secret information carried by each particle, determining the outcomes in advance. But decades of experiments, especially tests of Bell's theorem, have shown Einstein was wrong. There are no hidden variables. The particles don't carry predetermined answers. Before measurement, both particles genuinely exist in superposition, and their properties are genuinely undefined. The entanglement is real. Measuring one particle doesn't send a signal to the other. Instead, the measurement collapses the shared wave function, instantly defining both particles because they were never truly separate. Think of it this way. You have a pair of magic coins. You put one in a box in New York and one in a box in Tokyo. When you open the New York box and find heads, the Tokyo coin is instantly tails every single time with perfect correlation. Classical physics would say each coin was already heads or tails before you looked. You just didn't know which. But quantum experiments prove that's not what happens. The coins really were in superposition, both heads and both tails simultaneously, until you opened one box. The act of opening one box collapsed the shared superposition for both coins at once, no matter the distance. This isn't magic or telepathy. It's what happens when you take the relational nature of reality seriously. The two particles don't exist as separate things with their own individual properties. They exist as parts of one entangled whole. Distance doesn't matter because the wave function isn't a physical wave rippling through space. It's a mathematical description of possibilities, and possibilities don't have locations. When the wave function collapses, the entire state updates instantly because it was one state all along. Entanglement shows that quantum mechanics isn't just weird because of measurement or superposition. It's weird because the universe is fundamentally non-local. Events here can be correlated with events far away without anything traveling between them. The web of relationships that makes up reality can connect things across space in ways that seem impossible from a classical perspective, but are perfectly natural. Once you accept that particles aren't independent little balls, they're threads in a vast, interconnected tapestry. Now you can see how everything fits together. Wave-particle duality shows that quantum objects don't have fixed natures, they're clouds of possibility. Superposition describes how those clouds can include multiple states at once, existing simultaneously until interaction forces a choice. The observer effect explains what happens when that choice occurs, how interaction collapses possibilities into definite outcomes. And entanglement reveals that these processes aren't happening to isolated particles, but to interconnected systems where measuring one part instantly affects the others, no matter how far apart they are. There are four aspects of one consistent picture. Reality is made of relationships and possibilities, not objects and certainties. The universe at its deepest level is probabilistic, not deterministic. It's interactive, not static, and it's unified in ways that distance and separation can't break. Once you see this, the common misconceptions fall away. Quantum mechanics doesn't say your consciousness creates reality in some mystical sense. The observer effect is about physical interactions, not minds. Any device, any particle, anything that interacts and creates a record can collapse a wave function. You don't need awareness or intention. The universe was collapsing wave functions long before humans existed. Similarly, quantum mechanics doesn't mean anything is possible or that you can manifest things by thinking about them. The wave function describes real probabilities based on physical laws, not fantasies. An electron can be in many places, but it can't be in places the wave function assigns zero probability. The rules are strange, but they're still rules, And quantum effects don't scale up to everyday life in obvious ways. You are made of particles that obey quantum mechanics, but you contain so many of them, interacting so constantly with the environment that quantum superpositions collapse instantly. The world looks classical, solid, definite, deterministic, because decoherence happens too fast for us to notice the underlying quantum fuzziness. The rules never change, but their visible effects do. Understanding this transforms how you see the world. Even if you never calculate a wave function or run an experiment, you realize that what seems solid and fixed is actually a dance of probabilities resolving through interaction. You recognize that observation and participation matter, not because they're magic, but because the universe is relational at its core. Nothing exists in isolation. Everything is defined through connection. This insight powers real technology you use every day. The transistors in your computer and phone work because electrons can tunnel through barriers, a purely quantum effect where particles pass through walls by spreading out as waves of probability. GPS satellites carry atomic clocks that measure time using quantum transitions in atoms, jumps between energy states that only exist because electrons in atoms are quantized, stuck in specific superpositions of being in different places around the nucleus. Lasers function through stimulated emission, a process where photons in identical quantum states trigger atoms to release more identical photons, creating coherent light. MRI machines detect quantum spins of atoms in your body. Solar panels convert light to electricity using the photoelectric effect, where photons kick electrons loose one quantum interaction at a time. Even beyond technology, the quantum worldview offers a different way to think about uncertainty, connection, and possibility. You learn that not everything can be known or controlled, not because we're ignorant, but because reality itself is open-ended until interactions nail things down. You see that the universe is deeply interconnected, that what happens here is woven together with what happens far away in ways we're only beginning to understand. And you recognize that engagement matters. How you interact with the world, what questions you ask, what measurements you make, these things participate in shaping what becomes real. This is the power of the one big idea at the heart of quantum mechanics. Reality is relational and probabilistic. Once you truly grasp that, the confusion melts away. Superposition makes sense because if things are clouds of probability, of course they can include multiple states. The observer effect makes sense because interaction is what turns abstract probability into concrete outcome. Entanglement makes sense because if reality is fundamentally relational, particles that interacted once can remain part of the same system forever. The quantum world isn't a bizarre exception to normal rules. It is the normal rules, the deepest ones we know.